Okay, this last topic is a question or an issue that's only covered usually on one or two AP questions, but it takes quite a bit of understanding to really get it. It could take 2 or 3 class periods to do this. Since we don't really have that much time, I'm going to cover this in a video through the solving of several problems. So if you're watching this, congratulations, you're interested, and take your time, go through these problems slowly, and see if we can get to a place where we understand the LaGrange error bound. So the first problem we'll look at says, given f and g are differentiable functions on an interval ab closed, and f of a equal to g of a, f of b equal to g of b, it follows from the mean value theorem that f prime of c is equal to g prime of c for some c on the interval a to b. Explain this reasoning. So what we're going to do first, to use the mean value theorem, I need to create a difference quotient using a and b in this case. But I don't know which function to use. Do I use f or do I use g? And the reality is here you're going to construct a function called h, which is going to be the difference between f and g. So h of x equals f of x minus g of x. Now from the given information, they say f of a is equal to g of a and f of b is equal to g of b. This means that both h of a and h of b must be equal to 0. Because if f of a, if f of a is equal to g of a, then you'll subtract those two and get 0. Same thing if f of b equals g of b. So we have two values for h. Now we're going to construct that difference quotient that we need for the mean value theorem to be useful. Okay, so again, mean value theorem says if a function is differentiable and continuous on an interval, then the difference quotient, h of b minus h of a over b minus a, will be equal to the derivative of h at some value c, and c is a number between a and b. So we're going to use the mean value theorem on h. In this case, h of b we know is 0, and we know that h of a is 0. That means the numerator of this fraction is 0, and 0 over b minus a will be 0. This tells us that h prime of c is equal to 0. What is h prime of c going to be? Well, if we go back up here, h prime of x will be f prime of x minus g prime of x. So h prime of c would be f prime of c minus g prime of c. And since that's equal to 0, you can add g prime of c to both sides, and you end up with f prime of c equals g prime of c. Again, c is a number somewhere between a and b, and that's what you were asked to prove here, that there is a number where the two derivatives are equal. We're going to use this reasoning again in a little bit. But first, here's an illustration using some specific functions. So here they ask you to use f of x equals sine x and g of x equals 1 minus cosine x, whose graphs intersect at 0 and pi over 2. Okay, so what do they mean here? That's where they're talking about f of a equals g of a and f of b equals g of b. Okay, you have two places where the graphs intersect. So in this case, 0 and pi over 2. We'll see that picture in a second. This says there is a c, there is a number, between 0 and pi over 2 where the derivatives are equal. So again, that was what we proved here in this problem. There is a place where the derivatives are equal. F prime of c equals g prime of c. Okay, so first they say calculate c. So you would take the derivative of f. So since f is sine x, the derivative is cosine x. And the derivative of 1 minus cosine x is going to be just sine x. Now, I don't need a calculator to do this, but I'll just show you how you could use one to make things go faster. So you're going to set sine x equal to cosine x, ask the calculator to solve. And since these are trig functions, I wanted to limit the number of solutions. I put a such that bar, and I say restrict the solutions to be between 0 and pi over 2, since that's where we're looking, between 0 and pi over 2. The calculator returns to me pi over 4 as the answer. I didn't really need the calculator for that, but just to illustrate how the solver could be used. Okay, so this is saying that pi over 4 is the number where the derivatives of g and f are equal. Okay, illustrate this result on GeoGebra by graphing f and g and their tangent lines at c, and then sketch these graphs in your notebook. Okay, so here's what we're looking at here. The red curve is 1 minus cosine x. The blue curve is sine x. We notice that they intersect at a, that's 0, 0, and at b. That's pi over 2, comma 1. The theorem on the previous slide says that since these two curves intersect at two places, there's a number between them where the tangent lines will be parallel, where the slopes are equal. We calculated that to be pi over 4, and that's point C and point D, and we noticed that the two tangent lines in black are parallel to each other. So this is just a visual illustration of the previous slide's theorem on specific functions, cosine, 1 minus cosine x and sine x. Okay, now in this problem, we're extending the results of 2 slides ago. So it says, suppose f and g are twice differentiable. That means they can be differentiated twice and still get good values between a and b. Given that f of a equals g of a, and f prime of a equals g prime of a, and f of b equals g of b. So there's a lot of information there, but basically they're saying the curves intersect at a and b, and there's a place, and also the derivatives are the same at a. Okay, so that's what they're given. Show that f double prime of c equals g double prime of c for some c between a and b. So the second derivatives are going to be equal for some c between a and b. All right, hint. First show that f prime of k equals g prime of k for some k, where k is between a and b. All right, so what are we going to do here? Well, we have this idea that f of a and g of a is equal to g of a, and f of b is equal to g of b. So that's the conditions of this theorem here. If you have two intersection points and your function is differentiable, then there's a place between the intersection points where the derivatives are equal. Well, that's what it's first asking you to do. First, show me there's a place where the derivatives are equal. Okay, so the results from a few slides ago, we do the same idea. H of x is f minus g, and by the logic of 2 slides ago, there is a place where the derivatives are equal. Okay, so we won't go through all the details to get us there because we've already done that. H prime of x would be equal to f prime of x minus g prime of x, and since we know that h prime of a would be equal to f prime of a minus g prime of a, and from the given information we know that those two numbers are the same, h prime of a must be 0. Additionally, h prime of k would be f prime of k minus g prime of k, also equal to 0. So you may be able to detect what's already happening here. We're going to kind of follow the same pattern as we did a few slides ago. We can now apply the mean value theorem, not to h this time, but to h prime. And we'll use the values a and k in our difference quotient. So the mean value theorem says if a function is differentiable, and h prime is differentiable, because h is twice differentiable, then the difference quotient will be equal to the derivative, in this case the second derivative of h, for some number c, where c lives between, in this case, a and k. All right, so what do we have? H prime of k minus h prime of a over k minus a must be equal to the derivative of this function h prime, h double prime, at some number c, where c is a number between a and k. Notice that if you live between a and k, you also live between a and b because k is less than b. All right, and then the final step here is to notice that, okay, h prime of k is 0 from up here, and h prime of k is 0 from up there. So the numerator is 0. 0 over k minus a is equal to 0. So this tells us h double prime of c must be equal to 0. Who is h double prime of c? Well, h double prime of c would be f double prime of c minus g double prime of c. That's equal to 0. Add g double prime of c to both sides, and you get the second derivative of f at c is equal to the second derivative of g at c. And c is a number that's between a and k, which is also between a and b. Okay, so all we've shown so far is that if you have equal function values and now equal first derivative values, then you will have a place where the second derivatives are equal. Okay, and you're going to see that we're going to continue to extend this down the line, and that's going to lead us somewhere real soon. Next, we're going to look at an illustration of this with specific functions and specific intervals. Here we're asked to let f of x be sine x and g of x be 1/2 sine of 2x. These graphs intersect at 0 and pi, and the first intersection point, 0, they will have the same slope. That's what tangential means. So A says verify that the intersection x equals 0 is in fact tangential. So we can take the two derivatives of the functions and note that they have the same value. So f prime of x is cosine x, f prime of 0 would be cosine 0, which is 1, and g prime of x would be cosine 2x. The 2 from the chain rule cancels the 1/2, and g prime of 0 would also be cosine of 0, or 1. So the two functions f and g have the same slope at 0. B says there is a c strictly between 0 and pi, for which the second derivative of f equals the second derivative of g. That's the fact that we proved back here. So they want you to find this value of c. Again, we're going to jump to the calculator to do so. So here I set second derivative of f, which is negative sine x, equal to the second derivative of g, which is negative 2 sine of 2x. Ask the calculator to solve that, and again, I would like to restrict my answers to be between 0 and pi. The answer that is spit out is the arc cosine of 1/4, which is 1.318 roughly, and that is in fact between 0 and pi. So this is just an illustration of the theorem proven back here in this problem. This problem asks, suppose f and g are thrice, 3 times differentiable functions between a and b. Given that f of a equals g of a, first derivative of f equals first derivative of g, second derivative of f equals second derivative of g, and f of b equals g of b. So again, you have two intersection points, f of a, f of b, same as g of a, g of b, and then you're given that the first and second derivatives are the same for the two functions at a, the left endpoint. So this is going to have the similar form as the previous problems. We're supposed to show that the third derivatives of f and g are the same somewhere between a and b. And then we're going to write a general statement of what we've been doing in the last few problems, so we don't have to keep proving this over and over again. Okay, so how are we going to prove that this fact, third derivative of f equals third derivative of g? Same process as we've been going through. We're going to create this function h, that is the difference between f and g. The first derivative of h would be f prime minus g prime, and the second derivative of h would be f double prime minus g double prime. We've already established that there's going to be a value of k where the first derivatives are equal. That was several problems back. And then a few problems back, we established that there's a place where the second derivatives will be equal. From there, we're going to apply the mean value theorem on h double prime. Okay, so we're going to create a difference quotient with h double prime. So by the mean value theorem, we're given that h double prime of k2 minus h double prime of a over k2 minus a is equal to the third derivative of h, that's the derivative of the second derivative, at c, where c is a number between a and k2. Notice that if you live on the interval a to k2, you also live on the interval a to b. Notice that h double prime of k2 would be f double prime of k2 minus g double prime of k2, and since those values are equal, h double prime of k2 is 0, and the same goes for h double prime of a. So the numerator, once again, is 0 over a number, so the left side is 0. So that means the second derivative, or third derivative of h at c is 0, and the third derivative of h is equal to the third derivative of f minus the third derivative of g. Those are equal to 0. Therefore, the third derivative of f will be equal to the third derivative of g, somewhere between a and b. Okay, so we've done this now several times, so I think you will see the overall pattern. And what we want to say now, without a proof, is that if f and g are n plus 1 times differentiable, so we've been through differentiable, twice differentiable, 3 times differentiable, we get the same results essentially each time. So if f and g are n plus 1 times differentiable, and you have two intersection points for the graphs of f and g, and you know that the derivatives of f and g are the same at a. Okay, so if you have those facts, then you can conclude that there is a number between a and b such that the nth plus first derivative of f is equal to the nth plus first derivative of g. Wow. Okay, so we call this the extended mean value theorem. We've used the mean value theorem each time to go to the next step in this process. So you can tell we've really extended the mean value theorem's use here. All right, now why does this matter? We're going to get to that real soon. Just know that we can go as far down the line as we want, as long as your functions f and g are n plus 1 times differentiable, and be able to get to this fact. So here's another application using specific functions. So we're given f of x is cosine x, and another function, p of 2 of x, which is the second Maclaurin polynomial for the cosine function, which we've seen before. So part A says the graphs of f and p2 intersect at 0, but do not intersect when x equals pi. Confirm this using GeoGebra or your calculator. Okay, so here's the picture. The blue curve is the polynomial, and the red curve is the cosine function. You can see that they intersect at a, which is 0, 1, but they do not intersect at pi. This is the x value for pi, but should be down here on the red curve. But obviously the blue and the red curve don't intersect there. Okay, so we verified what they asked us to verify. All right. B says, show that there's a unique number k for which the graph of g, this is a new function g. What is g? G is the second degree Maclaurin polynomial, so that's the function up here, so 1 minus half x squared. All right, and then they tacked on a little extra piece here, k times x cubed. Okay, so we're supposed to find what is the value of k that makes this function g intersect f at pi comma negative 1. Calculate this k. All right, so that means if I plug in pi into f and plug in pi into g, they should have the same y value if we have the correct value of k. Calculator can help us do that. So we ask it to solve cosine of pi equals 1 minus 1 half pi squared plus this number k times pi cubed. Solve it for k. We get this number, 0.09465, etc. So if we use this value of k, then our two graphs, I should say our graphs of f and g, should intersect at pi. And here's the picture from GeoGebra to verify that. So the blue curve is cosine x, the red curve is the polynomial with the extra piece. They do intersect at 0, 1, and now they intersect at pi comma negative 1. Okay, so we've shown that it's possible to create this value of k, which gives you two intersection points, which remember is the key to starting the process of using the extended mean value theorem. Okay, after you confirm that f of 0 equals g of 0, okay, we've seen that on the graph. First derivative of f, same as first derivative of g. We know that's true because g is the second degree polynomial, Maclaurin polynomial for f, plus this extra piece. This extra piece is always equal to 0 for the first three derivatives. So that really does not affect anything. So g and f have the same derivative at 0, same second derivative at 0. So that's all good. Explain why it follows that f double prime of c equals g double prime of c equals 6k for some number c between 0 and pi. So essentially, this is what we did on the last screen. You have f and g being 3 times differentiable. They have the same value at a and the same value at pi based on this value of k. So that means there's a number c between a and b such that their third derivatives are equal. And the third derivative of g, if you do it 3 times, the polynomial part will wipe out. The 3 comes down, the 2 comes down, the 1 comes down, then the x disappears, and all that's left is 6k. Okay, so we have the third derivative of g is 6k. The third derivative of g is going to be equal to the third derivative of f at some place c between a and b. That's based on the previous screens that we've seen here. So if you solve for k, that means k is going to be 1/6 times the third derivative of f at c. That's part D. It says conclude that f of pi must equal p2 of pi plus 1/6 f triple prime of c pi cubed for some c between 0 and pi. Okay, so we're at the point now where we know what the extended mean value theorem says. And now the question, I guess, is what's the point? Why does it matter? So here's the reason. We're going to start by saying we know that a function in its nth degree Taylor polynomial p at some place that we chose, a, have matching derivatives at x equals a, up to the nth degree. Now, we know we use Taylor polynomials to approximate function values because the Taylor polynomial snuggles with the graph of f pretty well. So a natural question is, well, they snuggle, but how good is the approximation? How good can I guarantee this approximation is? The extended mean value theorem is going to help us answer that question. Okay, so let's just suppose that f is a function that is n plus 1 times differentiable, and p is the nth degree Taylor polynomial for f that's centered at x equals a. We're going to build this little function here, e of x, which is the Taylor polynomial of degree n, plus this little extra term here. We did this extra term a few slides ago. So this extra term has an extra degree of x minus a and is a constant. Now we're going to choose the constant k so that f of b is equal to e of b. So in other words, this e function will match the f function at this point b. We'll solve for b, we'll solve for b in a second, but the point of that is knowing that you have a and b where the functions have the same y values, we can start the process for the extended mean value theorem. Okay, we needed two endpoints where the values of the functions were the same. Okay, so we say note that e and f have matching derivatives at x equals a up to the nth plus first degree, and if we choose the correct k, we'll be allowed to begin the process of the extended mean value theorem. So the extended mean value theorem says if two functions have the same values at endpoints a and b, then you can find a place where the derivatives are equal between a and b. And since f and e are n plus 1 times differentiable, we can do this n plus 1 times. What happens to e after n plus 1 derivatives is everything disappears except for the k and the powers of n plus 1 and n minus 1 that came down by doing the power rule. The polynomial eventually disappears after n plus 1 derivatives because this only has n plus 1 terms that wipe each other out once you take derivatives. So what's left is k times n plus 1 factorial. Remember that e and f have to have equal derivatives at c, where c is a number between a and b, by the extended mean value theorem. This lets you solve for the mysterious value of k. So k is going to be equal to the nth plus first derivative of f at some number c that we don't know over n plus 1 factorial. Okay, so that's the extended mean value theorem. What does that get us? Here's what this gets you. It gets you that the function value, remember f is the function that we're trying to clone, function value for f at b is equal to the Taylor polynomial for f at b plus this little extra piece, which comes from up here. Okay, so you have the nth plus first derivative of f at this number c, which we don't know, but we know it exists, and we know it's between a and b, times b minus a to the n plus 1 over n plus 1 factorial. Now this is kind of remarkable because remember, f is a function that we're trying to clone. It has a series that goes on forever. If you cut off the series, you have a polynomial of degree n. So that's what the p of b is. This little equation says that that infinite series is equal to the polynomial plus one more piece. So this one more piece represents all the pieces that you hacked off. Okay, the only trouble is we don't know what this value of c is. So we'll get to why this is useful in a second here. Okay, so in English it says the function value is equal to the value of its Taylor polynomial. Before, but today it's been approximately equal to this, okay, plus the value of this special term. Okay, so the special term is the whole key because it represents the error in the approximation of the Taylor polynomial to the function. Okay, so big deal. Where do we go from here? It's all about this term, this extra term. Okay, so I'm going to make a note here that when you calculate this out, all of these symbols are known except for one. You're going to know the a value, you're going to know the b value, you'll know what n plus 1 is, you will know what the nth plus first derivative of f is. The only thing you won't know is this mysterious value of c. And all you know about c is it lives between a and b. So everything in this expression is numerical. However, we don't necessarily know the value of c. So this term only tells us something if we can bound the nth plus first derivative on the interval a to b. In other words, can I tell how big this could possibly be in absolute value? If I can do that, then I can put a bound on the error when I use the nth plus nth degree Taylor polynomial. So what kind of things can you bound? Well, with our knowledge of mathematics up to this point, we can bound a few types of functions. For example, If your derivative involves sine or cosine, you know that sine and cosine can't be larger than 1 or smaller than negative 1. So you can put a bound on those type of functions. If you know that your function is always increasing or decreasing, then you know that the maximum value either occurs at the right endpoint or the left endpoint. Okay, so let's go ahead and jump into two examples to see how this actually plays out. Use the fifth degree Maclaurin polynomial for sine x to approximate the sine of 0.25, which is a nasty value that we could not do without a calculator. Put a bound on the error of this approximation. Okay, so this process is called the LaGrange error bound. That's how the AP test will refer to it. So what they want is, what is the approximation for this number using the Maclaurin polynomial, and then how accurate can you guarantee this approximation is? Okay, so first of all, the Maclaurin polynomial for sine x, just to review, is x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. If we jump to the calculator and do the approximation for the sine of 0.25 comes out to be 0.2474, etc. Okay, so we'd like to know how accurate that potentially is. All right, by the setup on the previous two slides, we know that the error is going to be less than or equal to the value of the sixth derivative of f at some number. I put z in here instead of c, but it's still some number between a and b. Okay, times 0.25, that's the b value. A value here is a, so you don't see it because it's minus 0, to the sixth power over 6 factorial. Again, we don't know where this value of z is. The question is, can you put a bound on the sixth derivative of f? Who's f? F is sine x. I put a bound on this little highlighted term. Okay, so the sixth derivative of sine x is sine x. The largest and absolute value sine x can be is 1. So you can replace this term up here with the number 1. It tells you that the error is going to be less than or equal to 1 times 0.25 to the 6th over 6 factorial. All right, now this is kind of neat. So if you actually calculate that out, the calculator says that your error is going to be less than this number here, which is 1, 2, 3, 4, 5, 6 zeros, and then a 3. It's pretty darn accurate. And if you go back and then actually calculate the actual error, okay, so sine of 0.25 minus the polynomial, at 0.25 you get this number here, which has 1, 2, 3, 4, 5, 6, 7 zeros, and then a 1. So you were able to guarantee that the accuracy was at least this good. In fact, of course, it's going to be better. Okay, a second example. Use the third degree Taylor polynomial for square root of x. Centered at x equals 4. Use this to approximate square root of 4.2015. Put a bound on this error. Again, that's the LaGrange error bound. Okay, so we can't really do the square root of 4.2015 by hand. So we'd like to use the Taylor polynomial to approximate this and then be able to tell somebody how good is this approximation. So first we set up the third degree Taylor polynomial for the square root of x. If you use this to approximate the square root of 4.2015, you would get 2.0497, etc. So now we want to go through the process of putting a bound on the error of this approximation. So the error is going to be less than or equal to the absolute value of the fourth derivative of f at some number c between 4 and 4.2015. We don't know the value of c. That's why we're going to have to put a bound on this term here. Times 4.2015, that's the b, minus 4, that's the a, to the fourth power over 4 factorial. So the question now is, what is the bound? How big can this little term be between 4.2015 and 4? So first of all, the fourth derivative of the square root of x is going to be negative 15/16 x to the negative 7/2. So it's either greatest in absolute value at the right endpoint or the left endpoint. This is the x-axis up here, so we can tell that the greatest in absolute value this function gets is at the left endpoint. So that's what I will use to replace this fourth derivative of f at c term. So that would be negative 15/16 4 to the negative 7/2, 4 to the left endpoint. So our error is going to be less than or equal to negative 15/16 4 to negative 7/2 times 4.2015 minus 4 to the fourth over 4 factorial. Crank that out, it comes out to be this number, which is 1, 2, 3, 4, 5, 6 zeros, and then a 5. So this tells me my approximation is pretty darn good. And then if you actually calculate the error between the square root of 2015, 4.2015, and the polynomial value, you will get 1, 2, 3, 4, 5, 6 zeros, and then a 4, which this number is definitely smaller than this number. Okay, so this process is very cumbersome. It's very tricky, but that gives you an idea of how good a Taylor approximation is to the actual function value.